this mean we can do the thing about the, if we did well in the midterm, we can skip the final, or?
Since I have not finished grading, so the no.
Okay. What about taking the highest of the two instead? What about just taking the highest of the two instead?
What do you mean?
Highest in the midterm and final, instead of averaging.
I wouldn't
You need to
average
drop
it.
one.
Yeah, have a drop grades.
If you can write me an algorithm and code for me, so we can do the calculation.
I can do it.
Yeah, it's Excel.
I can
Highest
just
of
use
two.
Canvas. I'll do it. It's on Canvas. It's really easy.
No, I don't know. I don't want to use Canvas, but I want to see who can write
That's
the
what
book.
Canvas is made for.
I never use that.
Are you asking so you don't have to physically go through and see what the highest grade is? Like the algorithm you're talking about is
Yeah,
right?
I type it in and then you can do some calculation. Anyway. How's everything going with your qualifying exam? How many of you passed? None of you passed?
Only Sam passed.
Huh?
Only Sam did.
Who?
What's that
Sam.
class?
Who is Sam?
The guy.
The genius guy.
I don't know who is Sam. Anyway, you can see that I don't know your name. When I grade your homework, when I grade your midterm, that means I'm not biased at all. The final exam very easy. She said I only have 6 pages. That's not too much. How was my postdoc talk last week? It's awful. Okay.
Good.
They can let me know awful. You told
No,
me
he's
it's awful.
good. He's good.
Oh, seriously?
Yeah.
If you think it's good, if you think it's awful, let me know anonymously. Okay. And then, if you give me any feedback, it's not good, you don't understand what you're doing, I'm going to kick you out from my group, okay?
Wow.
Okay.
I don't have much money left in my group, so I need to think of to lay somebody else. Next year.
Who has all the money?
Huh? What's that?
Who has all the money?
Who has all the money?
Yeah.
The
that's my
one-
question. Like, MIT professors or like?
No. The professor's not rich. I mean,
No. I'm not talking about personal. Like lab funding. Who have all this funding?
who has all the funding?
Yeah.
That is the you need to
Who
ask.
say? Which professor usually says like, yeah, I have.
You need to check
For
with our dean, Michael. He knows. I don't know. I don't have his document, but I'm very
Because I
sure.
heard from every professor, we don't have funding. We don't have funding.
I don't have funding. I mean, for 2 reasons that professor told you they have no funding. One thing is that they really have no funding. The other thing is just an excuse don't want to bring you to lab. Oh, I have no funding. I'm doing the same thing.
Oh, the
I mean,
second
if
one?
I really like one of students, I will try to persuade somebody to give me fund to support student. If I don't like, I have no funding, although I have $1 million in my pocket.
So you are giving second excuse?
What's that?
You're giving second excuse?
No, I really have no money right now.
Okay.
Remember one thing, I mean, when you argue with your supervisor to raise your salary or whatever, so that's really what I'm doing right now. Everything transparent to you guys. And let me tell you the by the way. Typically, for each of the branches, NSF, NIH probably higher, DOE, DOD, every year, we can have, for each single CI, we can have 100K for each year. Okay? So what is your salary, graduate student? How much you got paid?
$17 an hour.
I think
No.
average of
PhDs
25,
get more.
25K a year.
PhDs, okay?
25K.
How much?
25K a year.
25K, okay? And then your tuition.
Maybe.
10.
Either way, because we are paying it.
Yeah.
How much do you pay for tuition? 10. Okay?
Yeah.
And then this is how much? This is 35K, okay? And did you know that you also have the fringes? Okay, fringes, then we need to pay roughly another 100K for the fringes for you.
For the course, it's 10K or it's 5K around?
But that is fine. I mean, doesn't make much difference. Okay, this is the money we're going to support you, okay? That is 45K. You think that's only half, right? And then on that, the university will charge 55%. This is overhead. That means whenever we spend $100, the university is going to charge us $53.5. Okay? That means the total price we pay on you is times 1.535. Okay? How much is that?
100.
Huh?
100.
It's not 100. You can check. Okay? It's around 70. Okay?
Oh,
Okay, this is what we have. Okay? And then we have 300K left. So to make sure that you can do the project, we need to spend on the last supplies. Okay? People, if I do a budget, I do 1K. Only 10K for the research. Okay, for the research. And then you need to support your traveling. And if you come to me, talk, okay, I also need you to pay me the registration fee, whatever. But remember, this is 10K we use for the experiment. But still, on top of that, universities still also charge 5.35K. Okay, we also charge over that. Okay, that means for the experiment we spend 50.35K. Okay, that means we only have 10K left. Okay, and out of that, you know how much we get. For me, you know how much I get from this one. I get about 5K. You know what I'm saying? So you don't think, okay, doctor, you got money. This is what we get. And this is how much we pay for each of the students. Okay? Huh?
That 5K, is that in addition to your salary? You have a set salary with the university. Is that like a commission basically on the landing grant?
Our salary is 9 months salary.
Yeah.
And we have 3 months of
I
the
think-
summer.
I think, is it fine to disclose all these things?
It's fine, it's fine.
Okay.
It's not, I mean, everything is disclosed because in Florida, all the payment for government employee you can find online.
Yeah.
Okay, everything online. So we have 9 months salary, and then we have 3 months summer. But from the grant, we can at most support ourselves for 2 months. And then we still have 1 month unpaid. Okay? But think about you guys, if you have 1 month unpaid, what will happen? You're going to come to the office and try to argue with me very hard, but we always have 1 month unpaid. You know what I'm saying?
So we have 11 months?
Huh?
We have
We
11
pay 11 months. If we have grant, even if we have grant, we only pay 11 months.
You
We have 1
overlap
month
separate
salary.
grants?
Huh?
Can you use 2 separate
No,
grants?
in
to cover
total. If the grant from NSF,
that? Yeah.
from DOE,
Okay.
in some, 2 months mostly.
Okay.
Okay? That means if you want to cover all of them, well, I mean, we need to find some other resources. We need to find other resources.
Like
CNC
industrial-
grant money?
Like for the company,
Industrial project?
Industry
industry
stuff?
project.
Okay.
But that, I mean, for the engineering department, yes, we still can find industry money. But for the Department of Science, they have no money. So think about it, okay? So that I disclose all this one. It's just not to tell you that is basically this is how much we pay your salary.
But why the 53.5?
Because university need to make the administration make sure the operation. When you go to the lab, you talk about okay, the lab is safe. We have fuel hose, we have electricity, we have what this one, all right? Who is taking care of it? Is the administration of the university, right? People, I mean, the EHS, the environmental health safety, come to check lab every day. If you have any requirement, they respond to you immediately, okay? We need to pay them.
I thought they took like just half off the top of the grant. They charge you to, do they do both of those things? Do they take, like, if you land a grant for $100,000 from the DOD, doesn't
Yes.
UCF come in and take 50,000 right off the
Yeah,
top?
exactly.
Do they still charge you the 1.5?
No, for
Like
example,
you-
you have, that means if you have 10K
Yeah.
come to your pocket, and the university automatically take about 1/3 of it.
Okay, that's right, yeah.
Yeah, you know what I'm saying?
But then they still charge you just a service fee that's 1.535?
Yeah. That's the, no. This is all removed. That means you have 10K. That means the available fund for you is only around 7.5K for you, okay? Because the university takes the overhead away.
So it's already deducted?
They already take.
Okay.
So this is the situation, okay? So we are trying our best to increase your salary, want to release your burden, but it seems like not the case. The other thing, always keep in mind, you work here for 4 or 5 years, hopefully 4 years, okay? In my group, I encourage students to finish the job in 4 years and graduate, okay? Because the university doesn't say that you have to stay for 5 years. And I don't want to keep students for more than 6 years. Because think about it. If you stay in a single place for 6 years, you are not productive. And then another one, do you think you can generate a national science paper in the next 1 year? It's impossible, right? And if you already get a lot of very fruitful results within 5 years, why do you want to stay in this place? You want to go to a better place, Stanford, MIT, to go to postdoc. I mean, don't laugh at me, serious, or go to industry, right? So 5 years is very reasonable time scale for everybody. If you can make it, congratulations. We want you to go to a better place. If you cannot, we don't want to waste your time and waste my time, right? But of course, if you can finish up in 4 years, perfect. You know that I have one student private back to Georgia, graduating in 4 years. Right now, he's already a professor. I mean, this is something. The reason I'm telling about timeline is because you don't worry too much about the salary. Try to save, try to enjoy life, try to work hard in your lab, and try to focus on research. Only 5 years. Although you are very poor, I know you have struggling financial issues for 5 years, but it's only temporary, right? It's not a permanent job. It's not a permanent job, right? We want to use the money to sustain your fundamental organic activity, right? To make sure that you still alive, okay? But after that, we hope that we move you to the next level, you know what I'm saying? So that's what we can support right now. But we're trying our best, right? But right now, you know that this is what happens. And the other thing is that for a typical National Science Foundation, this is most of the money come from for the university. The project, not 5 years, it's 3 years. Okay, it's 3 years. The NSF is 3 years. NIH probably longer, but typically 3 years. The NSF, DOE, and sometimes the DOD project, 3 years. Okay, what that mean? That means we need you to give us deliver result within 3-year time frame. And then we use the result to apply for another money to continue your research. Because your PhD 5 years, right? But the grant only support for 3 years. But if you do not deliver any result within 3 years, we have no way to continue the project. That's the reason why you can find after 3 or 4 years, the lab probably cannot support you anymore. This is because we don't have delivery. If we don't have delivery, we don't have grant to continue your job. I mean, this is probably, for NSF, DOE sometimes, you can ask a little bit more, but for DOD, no. I mean, they even can cut your funding within 3 years. They can cut the funding every quarter. You need to give them the report every quarter. Okay, even if they find that you not make the promise, they cut me immediately. This is how the research work. Okay.
But nowadays they're only giving 4 years program duration.
I mean, this is very rare. Okay, NIH probably.
No, I got like 4 years timeline.
I don't know, probably different agents. But for NSF, DOD, DOE, people is 3 years. People is 3 years.
Oh no, like when we apply for PhD,
Huh?
they mention officially we get 4 years to finish our PhD
Yeah,
from the department.
because the first year, typically you have TA or something. You know what I'm saying? You can get a TA
Yeah,
job.
but you said it's for 5 years, right? Basically they take it for 5 years.
That's the reason I'm saying that. The university do not have tell you that you cannot graduate in 4 years. But typically, people need 5 years to finish your job. Because first year you have a lot of class to take, right? And you need to go through the training. Okay, 5 years is very typical. That's the reason I told you if you can finish in 4 years, I'm okay with it. Okay? But in 3 years, no way. You even cannot finish or qualify yet, right?
But Professor, then how some of the professors in civil department are giving masters and PhD in 3 years?
What's that?
Some professors in civil engineering department, they are giving masters and PhD in 3 years.
The masters, of course, in 3 years. But I'm not sure. Oh, there's one scenario that if you already have master degree, you can transfer the credit. Okay, in that case, it's possible you can finish your PhD in 3 years. But the thing is, the bottom line is, we need to have the result, for the scientific research result. You know what I'm saying? Make sure that group can sustain. You know what I'm saying? So this is basically challenging for us, okay, also for you. That's the reason. So why I'm talking about that a lot, but I just Because this is the last class, we don't have much to talk. Let me tell you the funding. What about the funding, how the university is managing to do the job?
But Professor, I have a question, like,
Uh-huh.
you got a lot of nature papers, right?
I don't have a lot of nature
Oh,
papers,
you
who
have.
tells you? No,
I
no,
already checked your profile, okay.
No, I don't have a lot of nature papers.
No, but I saw you have like around 9 or 10 nature papers, right?
Together.
Yeah, but like after having this profile, like why did you select this year? Because it's good, it's really good, it's very good, I know. Because of the weather?
The thing is, you have to think one thing, okay? So it's just like a market. So if some area, okay, is very hot, that means also a lot of people in this area, right? Then of course university have a lot of opening, but it's also very competitive, right? And of course, some opening, you can say that probably only, for example, when I back to my PhD study, I was working on the atomic physics for several years, okay? Super cold atoms. It's not popular, okay? And the opening for that kind of the area, every year only about 5 or 10 opening, okay, position,
Throughout like,
and entire United States.
oh,
But the field is very small. Only probably less than 10 group actively working in this area across the entire United States. You know what I'm saying? But think about materials. Every year, if you count opening, probably more than hundreds of opening in different universities. Okay, but they graduate thousands of PhD every year. Right? So the same thing. I mean, if the area is hot, it's more competitive. If that's the reason. I mean, the area is hot, then you have quite a lot of paper. But think about the other thing. I cannot say that all the paper are useful. Okay, it's quite a lot of them are just hype and probably useless. That's what I'm saying last time. Okay, it's true that a lot of paper are just useless. Okay, but the thing is that without this kind of result, you cannot find which one is useful. Right? You have to give them the result first, and then people can select which one will eventually become useful or not. Right? Yeah, I mean, think about it. The same thing with the food you eat every day. How much percentage of the food can eventually digest and bring you into nutrition into the body? Not too lot, right? It's not 100%. If you have 100%, we don't need toilet anymore, right? But the reality is you have to have that one, and you have to have the fiber, right? You know that you cannot digest the fiber, right? But we need that one to make the healthy digestion system, right? But it doesn't mean that it's useless, right? It still meaning something, although it does not directly generate the product or any kind of actual value for the industry, right? But you cannot say that it's totally bullshit. No,
so that's why the Nobel Prizes are usually like announced after 40 years of discovery.
Yeah, exactly. But the thing is that right now, quite a lot of Nobel Prize also manipulated by quite a lot of other issues that like hype or whatever. You asked about the quantum computing. I don't have too much comments on it because I'm not the person working on the quantum computing or whatever. But I have some I'm a little bit conservative about the Nobel Prize. I mean, the other thing is that to chasing, I mean, what the Nobel Prize is doing, I'm chasing the hot topic. It's probably in the short period of time and get a lot of paper, but long term is probably not good for the development of your career. For me, like me, the same thing. I mean, when I joined this area, how many years ago? I joined this area in 2010. No, 2013 on the 2D materials, and that is still very hot. That's the reason I have. I mean, you're right. I mean, I have some nature papers or whatever. But the thing that at that time the area is very hot. But so far, if you still want me to do the same thing, you do the exactly same work, you cannot publish that paper to that kind of nature science anymore, right? Because the area, first thing is saturated, become more mature, and people know what's the limitation. Okay, at the beginning, people say, "Oh, 2D material probably the future of the world," and it's kind of continue the Moore's law to make the semiconductor industry go. I mean, continuous develop. Okay, it's everything flexible, whatever. But a lot of things that people got promised have not been realized for after how many years? It's already 20 years, right? We do not see quite a lot of application to 2D material yet, right? I know there's some application, but not the case, right? And I have no idea whether you attend the seminar from Rice guy, political giant, give us the talk 2 weeks ago. I think 2 weeks ago, right? I was his peer student, that's the reason I invited him. He was telling the truth. He was saying that, okay, you know, the carbon nanotubes, people already know that for how many years, for half a decade, but the application is still limited, right? But I mean, one thing is, it really takes time for people to find what's the application of it. On the other hand, if you have a better alternative, why do you want to focus on that material, okay? Here's one example. For example, I have no idea whether you heard of this one thing called dye-sensitized solar cell. Have you heard about it before? It's kind of like organic, inorganic hybrid structure. I mean, people invented kind of a dye to mimic the principle of the photosynthesis process in the leaf, okay? They can use the organic material to transform the solar energy into electric energy. Okay, they synthesize kind of like organic molecules. This is kind of a dye, red color. Okay, they coat this dye on some titanium oxide to generate electricity. The quantum efficiency of that one probably less than 20%. Okay, people spend decades to improve the efficiency of it, and then suddenly, one year is in 2000. I think it's in 2014 or 2015. Perovskite came. And probably just within 1 year, the entire dye-synthesized solar cell field died. Nobody working on it anymore. Because perovskite can easily go to quantum efficient over 15%. You spend tens of years, you only reach 10%. But within 1 month, that material already reached 15%. Why are you still struggling with that kind of material? Although, of course, there are quite a lot of scientific problems behind it, but it's not necessary for us to solve it anymore, right? And I went to the DARPA meeting last month. I mean, they're talking about the 2D materials and whatever. And the people have right now reached an idea is, as long as this job can be performed with silicon, stick with silicon, right? It's not about the silicon is the best, but definitely the cheapest so far, right? So I mean, that's really, I mean, especially when you do engineering research, the ultimate goal is not necessary to find the best system scientifically, okay? But our engineering point of view, you have to consider economy system. You have to consider the capability or industry structure people already established, right? For example, probably 2D material is better than silicon, but think about you need to start from the very beginning to build a plant, to design the architecture of semiconductor devices. So people will not do that, okay? Then you just redo the entire semiconductor industry. It's impossible.
But Professor, if you don't try, how new technologies will emerge?
You need to try, but the thing is, it won't happen probably even in decades. And that's the reason originally the Nobel Prize took a long time for us to verify. But so far, people simply do not need to verify because the fundamental innovation is really rare. You know what I'm saying? It's really rare. Think about the gravitational wave got predicted by Einstein. How many years later we observe it, right? But yeah, people believe that it's true. That's the reason people invest billions of dollars to see the gravitational. If they do not believe the gravitational wave exists, why they spend money on it, right? But think about how long it is, okay? But the principle of Nobel Prize that without verification experimentally, we never give the result to the theorist, right? But it's not the case right now, right?
But Professor, why do we spend so much money on this kind of research, like watching gravitational wave?
Because curiosity, right? I mean, that's the difference between us and AI. AI don't have the curiosity. We want to spend money to do something, although we think it's a waste of time, waste of money, but we still want to do, right? And that's the reason why, if you go to talk about that question, I mean, why we want to do all these kind of innovations and these techniques. I mean, do you think that you're living happier than Bob probably even 20 years ago? Probably not, right? You know what I'm saying?
But Professor, I have a MacBook 8 years ago.
I know you have MacBook, but you think about it. Without MacBook, how your father and grandfather survive? They don't have MacBook. They still enjoy life, right? I mean, it's not necessary. You always need to have this. That's the reason I don't want to replace my cell phone because there's a very cracked one. I think this is indeed an evil. Waste my time. You know what I'm saying? But I still stick to it.
You have a lot of gramophone in your home, right?
What's that?
You have a lot of gramophone in your home, right?
What's that?
The music system.
The music? What was the music?
I see.
I don't have one. Anyway, let me briefly go through what we need to cover on the final, okay? And then we can, if you want, we can continue the chat.
When is it due again? Is
Huh?
it December 1st or December 5th or?
What did I say last time?
December
25.
5th
So like to the 6th,
to the 6th.
like when it turns to 6 is when it's due.
Hold on. What I think I need the
The
deadline.
5th.
December 5th and 11:59.
I'm sure I talked about
Final
5th.
exam deadline
Yeah,
I wrote
is
down
on 6th.
it's on 6th.
Sixth,
So
yes.
when is the time I need to submit the final score?
Yes.
I think Professor December 9th.
No,
Okay,
I
then-
checked
Then you
yesterday.
want to give me the.
I checked yesterday. So
Okay,
it's
fine.
6th.
Okay, fine. Will work. December 5.
Okay.
Midnight?
Okay.
Yeah, but like a day.
Midnight.
Yes.
Midnight. Okay. Give that back to me. Okay.
And you're gonna release it today?
Yeah. Trust me, it should be an easy piece because I don't have much to cover. I don't
So
have much.
Professor, you will upload the portion now.
Huh?
He
You have
said
already
tonight.
uploaded the portion.
Tonight.
Tonight.
Okay. So yeah. Okay. So we have, as I mentioned last time, we only have the first part is about the fundamental thermodynamics. Okay. And the second part is all about the use of the Gibbs free energy, right? So we're talking about phase diagram. Okay. So the key point, phase diagram, okay? The key point is the phase diagram basically is we need to find a system which give us the minimized, the Gibbs free energy, right? So we give an example. The first example we mentioned is about the miscibility, not miscibility, is the miscibility gap. Okay, this is the most important. The concept in the class because this helps us to understand the phase separation or unmixing of the mixture. Okay, so we were saying that as the temperature going down, we have basically the Gibbs free energy is what? Is the entropy minus Ts, right? So we have two competition part. One is the entropy, the other is enthalpy, right? So as the temperature going down, this part becomes less and less dominant, right? Right? So then the effect from the entropy start to appear, right? For example, if you mix two things together, they don't like each other, okay? But when temperature is very hot, they still mix. But when you cool it down, since the contribution from entropy disappeared, it's got weakened, then this part is appear, okay? That's the reason. At the first, if you have mixed A and B, you have this Gibbs free energy, right? And the mixture gives you the smallest, the minimized Gibbs free energy. But when you increase the temperature, you start to have something like this, right? And then, if at the beginning, the mixture is at this point, then it's preferred to separate into two phases, right? And how do we determine the two phases? We just need to find this kind of tangent line, tangent to both values, right? And then this is one composition. This is the other this is the other. The composite, right? And as the temperature further change, you will start to see something like this, right? And you can see this tangent point keep moving, okay? And if you project this figure into the composition temperature, you will find that at this temperature, you have one phase here. And when the temperature keep lowering, you have one point here and one point here. And then we can get this kind of, we call it the miscibility gap, right? So this is the one thing you need to understand. And this is also a process. How can we plot the phase diagram from the Gibbs free energy curve as a function of T, right? So this is probably one question. This definitely will be included in your final exam, okay?
Are the two sides, the intersection of A and B, are they the same height?
Not necessary,
Oh.
not necessary in the same time. Of course, we also mention another concept, okay? Go at home and check this concept, is that in this range, we have two zones, okay? And this area is what? It's unstable, right? No, it's not unstable. Yes, it is unstable, but in this one we call it the spinodal area, okay? This one is the metastable area, okay? You need to know what's the reason why this one is metastable, why this one is the spinodal. This is the chart that I already mentioned in the class. Easy? This diagram. This is the first part, okay? And then this is the simplest. Example. We only talk about the misfit gap. And then we also make this one more complicated, okay? So then we start to talk about we have another concept is like we call it the lens diagram. Okay? Basically, lens diagram is what? Lens diagram is, this one is just like unmixing of solid, right? And then for the lens diagram, we start to talk about the phase separation, including the liquid and solid, okay? Including liquid and solid. Okay? Think about it. If we have a mixture, okay, mixing A and B, and then of course A and B can be both in liquid phase or in the solid phase. Okay, for example, like the liquid phase can have the Gibbs free energy curve looks like this, and the solid phase can have something like this. Okay, the reason is that liquid have higher entropy than the solid, right? So when the temperature going up, going down, the liquid will vary more significant than solid, right? At the beginning, the liquid is probably here, then everything is in liquid, right? And when you cool it down, the liquid is moving up, right? And then the solid phase starts to appear, right? And you can see that, but how do you find the minimum Gibbs free energy of this mixture? We still do the same thing, we do the tangent line, okay? And then you can see that right now it's not unmixing, instead is a phase separation between liquid and solid. Okay, we start to get a mixture of the liquid and solid, okay? And then as the temperature further going down, you can see that this kind of the tangent line, the point of tangent point also changes, okay? And if you project that one into the phase diagram, you will have what? At this temperature, you have these 2 points, and when the temperature going down, you have this point and this point, right? And eventually you will have something looks like it should be something here. And then when the temperature keep moving down, eventually you will have something like this. Okay? And in the between is a mixture of solid and liquid. And above is all liquid and underneath is all solid. Okay? And in between is liquid and solid mixture. Right? So basically follow the same procedure. Okay? As long as you know the position of the Gibbs free energy by doing the tangent line, you should find the stable, composite. Okay? And then project this point into the temperature chart, you will get the phase diagram. Okay? And of course, we can make the job more complicated, right? So for example, the solid Gibbs free energy looks like this, but the liquid looks like this, and the solid looks like this. Okay, and then when the liquid moving up, okay, when you do the tangent line, you have one tangent line, another tangent line, right? You have two, right? And eventually you will have something looks like this, right? You have miscibility gap, and then you have something looks like this. Because you have two tangent lines, you have two lenses, right? So something like this. Of course, you can make it more complicated, okay? We introduce the concept of, we call it the eutectic phase diagram, Okay, eutectic phase diagram. Eutectic phase diagram is what? Is a miscibility gap. It's so large, and it'll go across that one. Okay. Then the phase diagram all changes. Okay, it changes into this shape. It changes into this shape. Okay. So just change into the shape. Okay. So this one is actually is one lens. This is another lens, but this one is a miscibility gap. Okay. They overlap to each other and form this kind of line. And you can see that we have one unit point. Okay. And this point we call it eutectic. Eutectic point. Okay, I explain why we call it eutectic. Eutectic, U means well, and tectic means melt. Okay, that means melt well. Okay, that means although it's a mixture between A and B, but it's turned out that we have a single melting point. Okay. Although it's a mixture, but it's more behave like a single concept. You have well-defined melting point. Okay, but deviate from this point, if the mixture, the ratio between A and B deviate from that one, we start to go to this lens. Okay, that means we start to get some mixture between solid and liquid. But if you look in this area, all mixture melt together. Okay. So this is another thing you need to be careful. Okay. So basically, that's all the key points you need to remember for the phase diagram part. Okay. From the very simple miscibility gap and a very simple lens diagram, and then we have the different composition of them. Okay. If this solid and liquid they have in the center, then we have two lenses. Okay. And then if we start have the miscibility gap and miscibility is large, it's very large, and then we have this kind of eutectic phase diagram. So there's probably one or two questions on the phase diagram. Okay. Definitely, I already told you. One thing is that I tell you the variation of Gibbs free energy at function time, and we're going to use the curve to build the phase diagram. That is one question. The other question is that probably give one actual phase diagram and ask you to identify where is the eutectic phase diagram. Okay, something like that. You know what I'm saying? Ask you to read the phase diagram. But not very difficult, okay? Because as I mentioned, if we want to know more about phase transformation process, and from the phase diagram, this is the job for the phase transformation class, okay? It's not the thermodynamic class, okay? So we just go to a very superficial level of phase diagram in this class. Questions, comments? Okay. And then phase diagram, that's it. We only have one chapter about phase diagram. Basically, the phase diagram is just the application of the principle of the minimized Gibbs free energy. Okay, we want to find the composition which give us the minimal Gibbs free energy and to find which is the thermal equilibrium states. And with the same principle, we can also analyze the chemical reactions. Okay, so we have three. We mentioned about the three types of chemical reactions in our class. The first one is the reaction only involving gas phases. Okay. And the second one is the reaction is the gas phase and condensed phase. And the third one I mean, the first one only have the solid, only have the gas phase. The second one, we introduce one, condensed phase. And third one, we have multiple condensed phase, and the condensed phase are mixed to each other. Okay, that's the difference. And you will find that, if you view them together, you'll find that roughly the same thing. Okay. The key principle, the key idea to understand all this kind of reaction is for any kind of reaction, A plus B, for example. We have a reaction like this, right? We mentioned last time is the alpha A plus beta B react to generate what? Delta B plus what?
Omega W.
5. Yeah. Okay, something like this, right? So basically, we want to make sure that the system also has the lowest Gibbs free energy, right? The Gibbs free energy of the system is simply equals to, the sigma, GA, you just put them together, right? NA. Okay, just sum it together. You know what I'm saying? And when you want to minimize them, you just do the partial derivative. Okay, you just do the partial derivative. You just do the partial derivative. You get the equilibrium state. Okay, and by doing that, you will eventually find the equilibrium state of that one simply equals to alpha mu A plus mu B. From this one, we can get this result. Is the N, it's not N, is the alpha mu A plus beta mu B equals to delta mu C plus phi mu alpha. Okay, we got this simple relationship. So what that mean? Actually, what does that mean? That means, because think about it, if the Gibbs free energy reach the medium point, on this end is the left-hand side of reaction, on this part is the right-hand side of reaction. If you go move left, the Gibbs free energy is going to go up. If you move right, the Gibbs free also go up. And you have to move in the center, and then the right and left reach the equilibrium, correct? What that mean? That means if you have small amount of the A or B change into D or F phase, we simply do not change the total Gibbs free energy, right? That's why we have this kind of relationship, right? That means the total Gibbs free energy on the right-hand side and left-hand side equal to each other. That means we move small amount of this left-hand side to the right side. We do not change the total Gibbs free energy. And this is about medium point, because medium is always flat, right? Got my points? But that's only very tiny amount, okay? But if you change a lot, definitely we move to the right or left, okay? So we have this relationship. Basically, that's the key point, okay? That explains all this kind of reaction behavior, okay? For the gas phase, So I think at the beginning of the class, we already mentioned the Gibbs free energy. The Gibbs free energy of any ideal gas is a function of the temperature and also the partial pressure of it. Correct, everybody? And then if that is the ideal gas, we know what? We know the mu A is simply equal to, we introduce the mu A. Now mu A is what? Is the Gibbs free energy in the standard state. Basically, it's about 1 atmosphere. Okay? It's a Gibbs free energy of 1 atmosphere. And then from this one, we can simply add this term. Okay. Right, we just do the integration. Right? This from definition of the Gibbs free energy. We have this expression, right? This is 1 atmosphere, and then this is the mu at the partial pressure of A in the reaction. Then we have this relationship, right? Because we already defined the standard state as a 1 atmosphere. Then the ln PA non, this is 1, right? This term simply is 0, right? That's the reason we call it standard, because we just simplify the expression, right? Then we simply have this relationship. Correct, everybody? Right? This is the relation. Right?
So PA0 is 1 atmosphere.
P none is 1 atmosphere, yes. Okay, we put it back, Then we have alpha mu A none plus alpha RT ln PA and plus you pass it up, call it back. You are the only one. I'm going to fail his final answer. Right, we have this one. And then what do we have? I mean, we can also define the change of the standard, the change of the standard Gibbs free energy, or the change of the standard Gibbs free energy. Define something like this: is the delta mu non plus delta plus mu F non minus alpha mu A non minus delta mu B non. Okay, this change of the free energy. Okay, and then by using that equation, you can get something like this. Use what? Use what? Goes to minus RT log P F phi P D delta P A alpha and P B delta. Right, we have this one. Okay? Because this one is constant, right? This is constant. Actually, this one is not depends on the, this one is independent of the partial pressure of the reaction, right? Because all the chemical potential are defined in the standard state, basically 1 atmosphere, right? So what that means is, as long as you know the reaction, you can directly calculate the change of standard Gibbs free energy, right? And from that one, you have this relationship, and then you can calculate the partial pressure of everything inside reaction, and that means under reaction, under the equilibrium states. Got my points? Right? Basically, as long as it write down the equation and you know all the free energy, Gibbs free and the partial chemical potential of each component under the standard states, you should be able to calculate the partial pressure of each component, okay, by using this equation that determines the equilibrium of the reaction. Correct, everybody? That's simple. And then this is all the key information when you talk about the chemical reaction involved, the gas phase, okay? So here, as I mentioned, I probably just give you one reaction system, tell you the standard chemical potential of each component, and tell you the initial partial pressure and ask you to calculate what's the final product. Basically, this is your homework. Not a homework. Yeah, homework. Right? We have some questions about it. No, in the practice class, I think I already asked you to calculate something. Okay, roughly the same thing, okay? You have fundamental thing, okay? As long as you follow my class, you should be able to pass. Except you. Anyway, so we need to make everybody happy. Anyway, so what about solid state? What about solid state? Okay? So the same thing, even for the solid, for example, in this reaction, we only have one solid phase. Okay, for example, the F is solid phase, and all other are gas phase. Okay, just for example, not necessarily. Okay, and we still have this relationship. This is just from the very fundamental principle of thermodynamics. Okay, no matter what type of reaction looks like, we always have this relationship, right, to minimize the total free energy of the system, right? And from that one, we can also write this one. Okay, but here's another very important thing. For the solid phase, we do not have the partial pressure because it's solid. We cannot define partial pressure, right? And from practical, we mentioned about something like we can build a reaction that we vaporize this one, okay? And to assume that reaction is between ABD and vapor phase F. Right, vapor phase F, and then rebuild, and then use another loop to bring the vapor phase back to solid phase, right? But eventually you will find that the concept is very simple. You can simply ignore this one because there's no partial pressure, just ignore this one, right? Because you can assume that the chemical potential of solid is not very sensitive to the pressure. You can compress the gas, the volume change, right? But the gas, liquid or solid, you compress it, the volume doesn't change, the Gibbs free energy doesn't change that much, right? Because if you compress it, you don't change the temperature. You don't change the entropy, right? And the only thing you change is this term, right? VP, correct, everybody? And this one, P changes, but the volume doesn't change much. So it's very tiny, right? So basically, the contribution of the compression or to the entropy of solid is not significant. That's the reason we can simply ignore this term, okay? And then what do you have? You just make the modification, you just ignore this term. Okay? That's it. Okay? That's the only difference between solid phase and the gas phase reaction. Got my points? But the assumption only apply to the scenario that you only have one solid phase or liquid phase. But if you have multiple one, we have another issue, okay? That's about the third topic. For example, if you have the third one, if you have the solid phase, now A and B are both liquid, both gas phase, and you have D and F are solid phase. We don't worry too much about what kind of reaction it is, okay? It doesn't matter, okay? But as long as we have this kind of reaction, then things become complicated. The reason is, if you mix D, if D and F are mixable, if they can mix to form an alloy, we have another contribution, because when you mix them, we start to change their entropy. Right? Because it makes the entropy changes. Then the free energy also changes, right? So remember, then what do you need to do? What do you need to do? We mentioned, you should remember when I mentioned the mixing of solid. How do we calculate the change? We talked about the regular solution, we talked about ideal solution, right? And then we unify these two cases by introducing the concept we call activity. Right. Activity basically is similar to the partial pressure of the gas. Right? Then you just replace the partial pressure with the activity. And the whole relationship still holds. Okay? Basically, what's the activity? Activity is you just vaporize the solid state, right? Mixture. And then we measure the partial pressure of each component of the solid. Because if you vaporize it, the solid phase and the gas phase, or the solid phase and the gas phase are in equilibrium. Then they share the same Gibbs free energy. Then the partial pressure in the gas phase equivalent to the activity in the solid phase. Correct? Then we can just replace the partial pressure with the activity. That's it. Simple, right? I have no idea why we spent about 1 month to talk about that one. Okay, can one class.
You never explained it that well before.
What's that?
Why did you say it like that before?
I need to get my salary.
Right.
I need to give you the service to make you happy. It's not the case. The reason is, if I talk in that way without giving you enough background, you will think I got really frustrated. But in the summary class, I just changed the angle. Okay? You can see from the bird view to see the entire process, everything becomes very easy. You know what I'm saying? But we need to build up from the beginning. We need to introduce how we build up, what's the activity. if I just say, okay, there's no difference between all the three things, okay? So we can just replace the particle pressure with activity. Oh, what's the activity? Right, you don't know. Make sense, everybody? Yeah, simple. That's we'll cover all. That's all about your final exam. Okay. Now the cumulative. Okay.
You said it was or was not cumulative?
Not.
Not. Awesome. Cool.
As I mentioned, I want you guys to learn fundamental ideas. Make use of these fundamental ideas in your research. We pay your salary, you bring. Yeah, that's insane. Be very careful. We have one practice class, okay? We have one practice class. The one practice class covers the key points of the reaction, gas phase reaction and gas condensed phase reaction, okay? Go through it very carefully, okay? Think about it. We don't have quite a lot of real examples, okay? I do not want to artificially create any reaction. We need to go through the actual reactions, okay? But I am not a chemist. I don't know much reactions. So I can only pick up the established one or well-known one, okay? But follow the same principle, okay? Go through very carefully today, tomorrow, or yesterday, whatever, so you should be able to deal with your final exam. Okay? Questions, comments?
Never had time to cover the drag of ammonia reaction.
Oh, don't forget about it.
But you said it's going to be tested.
I'm going to remove it from final test. Ammonia. If you want, I can post online. Do you want to review that by yourself? I post ammonia reaction online. You can have a chance to see that by yourself, and then I can cover that in the final exam.
What if you posted those stack of papers online?
That's too much. That's too much.
Is it too much?
No, I'm
You need to
lazy.
be prepared.
I'm lazy. Okay, something else? Something else? Nothing? Okay, then I think we are pretty much for this semester. Thank you so much for joining my class and suffering from it. I hope you're not, okay? Because I know how the other professors talking about it. Okay, online student, though, you can feel free to go.
I ended up taking this class before I took my normal thermodynamics class.
Uh-huh.
What do I need to remember more?
What's that?
Or am I going to make it like, is normal thermodynamics going to be easy for me now?
Huh? I think so. I hope so. Because I mean, which department from?
Material science.
I hope so. I'm not sure about whether I'm ready with that class, truly. But I mean, thermodynamics typically we don't need to. I mean, you can make it very complicated, but the key point only that much. Okay, you need to understand what's the analytical, I mean the explanation about thermodynamics, and just make use of it. Okay? And eventually you can find the most important thing for us to use the thermodynamics to analyze the actual problems, to minimize the deep free energy. That's it. Okay? Actually, we don't talk about dynamic process. I mean, in the phase transformation class, we need to talk about diffusion. We need to talk about the energy barrier. We need to talk about the nucleation process. We need to talk about the like how the spinodal, I mean, the process actually happens. Okay, the dynamic process. But for thermodynamics, we simply do not go to the details. Okay.
Oh, isn't that like kinetics too?
Yeah. We do not talk about kinetics, right? That's really called the thermodynamics. Okay, we do not talk about kinetics yet. Anyway, so any other questions? Do you want to hear about more thing about how the university manages the grants or whatever? And how much you got paid from this? Right? I mean, you know that actually your salary is not the high, is not lower than postdoc. Your salary is not lower than postdoc. I mean, from what I pay, it's not lower than postdoc.
Postdocs usually get like 55,
They're saying they
60K.
take home more. and they
Fifth
get
postdoc. Remember how much I pay you? I need to pay you 70,
70 grand, right?
right? Postdoc, the base salary for postdoc is the 57K.
Yes.
Okay? And then that is right, but we also need to consider the overhead, right? But the reality is whenever I hire a postdoc, the university going to cover at least 27K.
From that 57K. So you
Yeah.
basically have to pay 30.
I only pay 30K,
Okay.
and then times 1.53. Okay,
That's
that
the behind
is
mathematics, right?
45K. Okay, the reason is university, the UCI want to boost the research. They want to hire postdoc to supervise the undergraduate students. You know what I'm saying? And then they want to boost the number of postdocs. That's the reason they pay. Okay?
Professor, why 1.5?
Huh?
Oh, that is
But you
extra.
still charge it.
That's in the overhead. That's in the overhead.
Paying to manage, maintain that.
Okay? That's the money we pay for the postdoc. And the postdoc, we don't want to pay them tuition. We don't want to pay them registration fee, whatever. Okay? And that's the reason postdoc cheaper than you guys.
But professor, like you can treat your PhD student like you can give them TA position sometimes for the
The
first
TA
year,
position-
fellowship.
The fellowship, I have no idea whether you still can apply the fellowship. I mean, I give one student a fellowship, but the turnout is still not sure. Okay?
But professor, this fellowship is from the university, right?
From the university.
Not from the professor.
No, the fellowship is from the university. And of course, if you are a US citizen, how many of you are US citizen here? You can apply for the NSF, NASA, DOD, DOE fellowship. Okay, that can save your profile a lot of money. Indeed. But if you're not a US citizen, unfortunately you cannot get it. Okay? So try your best to apply for that, okay? And the good thing is that you can also join quite a lot of the classified projects. For example, hypersonic. I think you're working on hypersonic, right?
No, I work directly on.
Oh, that's fine. Yeah, but still, you can join quite a lot of classified
He
research.
can't disclose, right? He's working.
You cannot disclose, but you can join it.
No, that guy, David Mitchell's guy, is one of the guys.
Yeah, but for the international students, no, you cannot.
You're working the hypersonic hip.
He is hypersonic.
Hip. Get it.
You know that I even do not have access to the building because I'm not a citizen.
No.
I'm not a citizen. I'm just a green card holder. That's it.
But soon you are going to get citizenship as well.
The citizen have another issue. I mean, when I have no connection, relevant, exist in my motherland, I just got a citizenship.
Okay. This is the problem.
Yeah. Yeah, that talk that much. The key idea is focus on the research. Don't worry too much about your low payment. I know your payment is very low right now. Focus on research. Spend 4 or 5 years here, work very hard, and then find a good job. Okay? You know that I have a friend, graduated from, got a PhD. Right now his salary is more than 500K a year. Right? I have another student younger than me. I was the postdoc and supervised student. Right now he's Apple.
Professor, why didn't you get a job in industry?
Said that's what he's trying to do. That's what he's
You know that the
right?
professors, they are smart person indeed, but not that smart. It's about the lifestyle, you know what I'm saying?
So
It's
if
about
the
us.
super smart guy goes to industry,
I'm not saying that, okay? I'm not saying anything. I'm just saying myself, okay? I admit I'm not kind of smart, but not the top list, okay? I'm not the most intelligent. That's the reason I do not. Anyway, okay, enjoy the final.
$99% of happiness can be bought with money.
You cannot modify major final.
Yes.
Alright.
My homework is fine.
You sure?
Don't fuck.
but if we don't.
I don't know, yeah, is there any heads up on, are people doing generally well on the term, if you got any? Alright, yeah, I'm kinda stressing out yet.
It's not like the university entrance exam, we don't screen somebody.
Okay,
Well, as long as you're doing well, we're going to give you the pass.
okay.
We don't want to give you a hard time.
It's not like our mark